Inside the hidden workshop that built the Thunderbolt's giant engine, the night looked molten. Steel doors hung open to spill orange light onto a yard that smelled of oil and wet earth. Inside, metal sang. Hammers fell like slow thunder. Sparks climbed in curtains, then scattered like a broken constellation. Men and women leaned into the heat as if leaning could press the problem into submission. A half-finished crankcase sat on a cradle, its outline washed in the fierce white of an acetylene torch. Molds steamed where they had been poured hours earlier. Smoke threaded between benches. The whole room seemed to breathe, inhale, exhale, with the pulse of blowers, gas jets, and the breathing of the people who kept the place alive. They were building something that the world had not expected to exist for the Thunderbolt. An engine of unusual size and power, a machine that would ask metal to do things metal had refused before. The directive came from voices far from the foundry, officers who drew lines on maps, designers who sketched wings and loadouts. But the work happened here, close to the floor, where hands judged the weight of a piston with the same certainty as a parent feeling a child's forehead. They had been warned. They had been told that such an engine would be too big, too hot, too temperamental. There were books thick with rules about how much pressure a crankcase could take, how fast a bearing could spin before the oil atomized, how cooling fins shed heat into the air. The Thunderbolt's demands tore those rules and left a question in the center of the room. If the textbook said no, could the workshop invent a yes? If you want more stories from behind the factory doors, like or subscribe. The need was simple in its urgency and complex in everything else. The aircraft designers wanted power, significantly more power, so the Thunderbolt could carry heavier loads, climb faster, and reach farther. Greater power meant larger cylinders, higher compression, more force on every connecting rod and bearing. It meant temperatures that could soften a steel wall if not properly managed. It meant vibration that could shake bolts loose and, in the worst cases, make whole assemblies tear themselves apart. How to make metal resist that violence? How to keep oil from breaking down at a pressure that would turn it into vapor? How to feed more air into the cylinders without cracking head gaskets or melting valves? Those were questions that did not have neat answers. They had experiments. They had nights that turned into mornings. They had people who would not walk away. At the center of the effort was Arthur Hale, a man whose hands were stained with the colors of furnaces and whose voice carried the calm of someone who had seen castings crack and fittings fail and yet kept returning to the bench. He had been a pattern maker before the war. His apprenticeship had been measured in chips of wood and the geometry of molds. He had learned metallurgy the hard way, by trial and by watching failures, then trying to make the same mistake in a slightly different way until metal behaved. Around him moved a cast of names and backstories. Maria Santos, a lathe operator who could find microns by the feel of a tool in her hand. Young Samuel Ortiz, who had joined to make his future and who tracked every run sheet with the intensity of someone who had lost a brother overseas and wanted his life to mean something more than grief. Thomas Reed, the draftsman who drew straight lines and then, over evening coffee, bent them into improbable ducts and impellers on a scrap of paper. Above them hovered Major Carter, an officer with little patience for uncertainty and a vocabulary of deadlines. The workshop answered to no single label. It was a network of skilled individuals and a handful of managers who coaxed resources and tolerated setbacks as if setbacks were currency. The rooms they worked in were not glamorous. They were practical, lined with pitted benches, racks of gauges, and bins of parts cataloged on yellowing cards. A scrapboard map showed suppliers, unnamed testing facilities, and an inked note. Priority, Thunderbolt engine, high. Behind that board, a closet held letters from home. A woman on the night shift dried her eyes with a rag and returned to a machining wheel. A man with a bandaged palm traced the faint signature that every technician left on the first casting that met requirements. A ritual to claim a moment when metal bent, finally, to the maker's will. From the beginning, failure was material and audible. Castings would seem fine until the first heat cycle, when hairline fractures opened like threads along a seam. Test stands would spin up only to cough and choke. The piston rings would seize, and the wood-framed house of a test cell would shudder under a thump that felt like a fist on the door. There were nights when an explosion blew out an inspection window and sent a plume of smoke into the yard so dense that the team had to step outside and look at the stars until the air cleared. Those explosions were not cinematic theatrics. They were calibrations of reality. Each failure taught a lesson. Each broken part described to those who would listen what the metal could not endure, and, by implication, what it needed. The team kept meticulous logs. Time of failure, last observed RPM, indefinido, temperature readings, indefinido, location of fracture, notes on casting porosity, and whatever few vibrations the instruments had captured. The logs were not cold. They were intimate. They bore sketches in the margins, arrows pointing to a microstructure, a note like, "Look here, grain separation," that would be argued over like a church sermon. The first sensory scene that became legend started in a foundry bay that could have been any other at first glance. At 2:13 a.m., the furnace was at a temperature written in the logs as indefinido. Flames licked the crucible's lip. Molds set in a circle around a platform. A set of new pistons, oversized, heavier, treated with a surface process that smelled of burning oil, glowed a dull orange. The pour started. The sound was a long, wet hiss, like rain hitting hot iron. For a half minute, everything seemed to move in slow motion. The molten metal spread like quicksilver. The edges took. Steam rose in ropes. Then a vibration rolled through the floor, a staccato rat-a-tat that people felt as a pressure in the chest. One of the molds cracked. A seam opened and disgorged a plume of smoke. And in the glare of the torchlights, the casting looked as though a seam had been cut into its side. They learned to listen to that sound as if it were a voice. "Porosity," someone whispered. Not everything failed on pour. Some castings matured, but then failed during a stress test weeks later when an impeller sheared itself free and sliced a valve. Others survived bench tests but failed at the first startup in a simulated altitude chamber where pressures and temperatures conspired to turn oil into mist and to strip heat too slowly from a head. Each failure widened the horizon of what they had to invent. The design team had proposed simple solutions and been rebuffed. Make thicker walls. Increase the musculature around the crankcase. But thicker walls meant weight that compromised aircraft balance. Change the alloy. Easier said than done. Alloys are recipes. Recipes are the domain of chemistry. And the chemistry available to the team was bounded by supply constraints, time, and the limitations of furnaces that could only reach certain temperatures. So they experimented, not in the abstract, but in the most physical sense, by mixing ingots of different metals on the shop floor, by trying a trace of an element in one batch and not in another, by forging samples, hardening them, grinding them to see the fracture surfaces, and reading the microscopic map of breaks. They sent samples to universities and back to corporate labs. They borrowed instruments, spectrometers, and scanning rigs when they could. When those were not available, they invented proxies. A flame test here, a simple tensile jig there. It was a choreography of ingenuity and scarcity. You could see the progression by following the scrap trays. The earliest trays held castings with ragged edges and obvious shrink lines. Later trays held parts that failed more cleanly, a kind of brittle snap rather than a diffuse tearing, evidence that the metal had gained strength in some ways and lost in others. The workshop learned to read these breaks as a physician read symptoms. They were diagnosing a patient who refused to keep the same disease twice. One of the most inventive minds in the shop was Thomas Reed, the draftsman who scribbled notes on cigarette packs. Reed had an eye for airflow. He watched the test stands like a hawk, noting where heat clung and where it fled. At a midnight lunch, he doodled a fan housing with a baffled duct that would channel air over cylinders in a way that was less blunt and more surgical. The idea was crude at first, just scrap metal and a drawing that looked almost whimsical. But it found traction when Maria, the lathe operator, bolted together a prototype from sheet metal left over from a wartime contract. That duct was one of 1,000 small inventions that started as jokes and then became necessities. It reduced the hottest spot on a cylinder head by what the team logged simply as indefinito. It shifted the way heat bled from the combustion chamber and altered the thermal gradient across a valve seat. No single one of these fixes was a silver bullet. They were incremental, they were patient, they were the sum of many hands. Then came the test cell explosions. Tests were ritualized. Before any run, the cell was swept, bolts were checked, fuel lines were inspected, a man with a clipboard read aloud the run sheet. Tolerances, expected RPM, indefinito, pressure watch set, emergency cutoff location. The engine would be strapped to a frame, instruments would be wired to its belly like veins, and cameras would watch spaces unreachable by humans. The team would step back into a booth behind thick glass and run it. Some tests were dull and faithful. Others were catastrophic. One particular night, long after the foundry had closed its doors but the testing bay remained lit, a prototype shoved at the top of its envelope. Gauges climbed, the sound layered into a humming roar. Instruments spiked, and then silence. A bright flare, then a concussive boom. The glass window cracked under pressure, and, for a moment, no one spoke. A technician stuck his head out and smelled the acrid tang of burned varnish. A pile of sheet metal had been torn free from a guard and curled like a cigarette butt thrown back by heat. When the men entered, half of the instrument cluster had been flung to the floor. A piston ring had failed, and the blowback had bent a valve guide. The photos later would show a smear, a black line across a bearing where oil had boiled away. Each explosion tightened something else: the schedule, the nerves, the budget. Major Carter made his rounds with a calendar and a thin smile. He asked for progress reports that read like promises. "We need it done by indefinito," he would say, and people translated that into longer hours, into deferments of vacations, into mechanics staying overnight on benches because sleep at home was less productive than sleep on the cold floor where you could be back at work at first light. The workshop took on a camp-like rhythm. Shifts overlapped, sandwiches were cold, and there was a kind of stoic humor that kept things moving. Samuel Ortiz collected the best of it. Small jokes scrawled on the sides of crates, because laughter was, in that place, a safety valve. The moral dimension of the work hung over every decision like a shadow. The engine they were building would, in operation, change aircraft capability. That change could be used to hasten missions or stretch raids. It could make aircraft faster, lift heavier payloads, fly farther. The men and women in the workshop did not talk about strategy much. They talked about bolts and bearings and whether a particular heat treatment left grain too coarse. But they were not blind. They knew that what they forged into being had consequences. Letters from pilots came in, some unsigned, some short, thanking the machinists for a job that let them get home. Other letters described what the missions had done in less flattering terms. The team folded those letters into folders and read them in the quiet hours. The instruments did not know how to measure moral weight. One night, after a failed start where the whole engine coughed and stopped at a fraction of the desired RPM, Arthur walked alone the length of the shop. The glow of the furnace had dimmed. A few lamps strung above workstations turned the metal on the benches into islands. He stopped at a crate and took out an old photograph. His apprentice class. Faces sunburned from summers at the pattern shop. He had been a young man in the picture. He tucked the photograph back into his pocket and leaned against a lathe. Somewhere in the building, a radio played low static, then a serviceman singing softly in a voice that barely held a tune. The work was technical, but the motive force that kept it going was human. Pride, duty, need, fear, stubbornness. As the months advanced, the approach to testing became more methodical. No longer were runs random forays into unknown RPMs. The team built step tests. Hold at a given RPM, indefinito, for a specified interval, watch temperature curves, note oil pressure. They developed instrumentation that would give earlier warnings of impending thermal runaway. They mounted thermocouples in blind spots, altered oil scavenging routes, and redesigned bearing housings to encourage oil to stay where it mattered. When a part failed, they replaced the whole assembly and traced the problem back through the chain of design and manufacture, from the ingot to the final machining pass. A breakthrough in method, if not yet in result, came when the shop changed the way it treated crankcases. The old method stressed large castings in a single pour, then attempted to reconcile internal stresses through heat treatment. Cracks often formed at junctions where loads concentrated. The new approach, still tentative and requiring custom jigs, used segmented castings that could be bolted and then welded to achieve superior grain orientation. It was messier, heavier in parts, but it reduced certain failure modes. The approach required a new set of fixtures, a different welding technique, and a sequence of post-weld heat treatments that were tested with a zeal that bordered on ritual. Each step in the process was logged and then debated over coffee. They tested shrouds that would protect cylinder heads from recirculation and ducts that would feed cool air to the rear of the crankcase. To support these mechanical innovations, chemistry had to change. New alloy trials began moving from small coupons to full-size forgings. The team introduced trace additions, small percentages, the exact composition listed in shop files as indefinito, that promised more ductility under high temperature cycles or better grain stability after repeated heat treatment. There was no guarantee for any batch. An alloy that held a tensile strength in a lab might harbor hidden carbides that made it prone to cracking in a real cylinder. The foundry staff learned to read micrographs and to interpret etching patterns as if reading topography. The most promising batches were set aside and guarded. Some were marked with the initials of the technicians who had overseen the pour. The practice was both pride and provenance. It was during one of these experimental sequences that the group made a symbolic but crucial decision: to run a long-duration endurance test. Endurance was not about raw peak power. It was about persistence, about the engine holding a steady output for hours while being pounded by heat cycles, while oil circulated, while vibration took its toll. Short bursts had been their story so far, moments of screaming RPMs and subsequent failures. Endurance required patience and confidence in every subsystem. The run was scheduled for a quiet morning. The team assembled like a congregation. Wires snaked from the engine to racks of instruments. Thermocouples were placed at known hotspots. Oil pressure transducers hummed. The plan was to bring the engine to a moderate RPM, indefinito, and hold it for an extended interval, indefinito. The goals were explicit: no spurious vibration, no unexpected temperature spikes, stable oil pressure, and no sign of material creep. What followed was the third sensory scene that would carry the team forward. Engines have moods.
This one, when it came alive, began with a low thrum that rose and balanced into a sound like a heartbeat. The gauges climbed into acceptable ranges and stayed. For the first hour, nothing remarkable happened. The professionals present were alert but not anxious. At hour 2, the sound became a steadier, deeper tone. The thermocouples read steady lines. A crewman stepped outside to pour coffee and returned to find the engine still singing as if it had been doing so for a lifetime. By hour 4, the room had a different quality. The hum filled corners and swallowed smaller noises. Faces under the arc lamps had the glazed focus of people who had spent nights in the same light. The oil-pressure graph had a slow, confident line. The temperature curves traced gentle hills rather than wild peaks. At hour 6, a warning flag flickered on a monitor. Anomalous vibration in cylinder 4. But the change was marginal and within a tolerance that had been pre-agreed.
The team decided, cautiously, not to shut down. They watched. The vibration eased. There was no dramatic burst of applause. There was no cheering. What was palpable was a lightness in the shoulders, a loosening of jaw tension, a very human exhalation. Some technicians wiped their faces. Some allowed themselves a smile. Arthur walked to the clipboard and signed his initials beside the run entry with a stroke that seemed to anchor the moment. Photographs of the instrument cluster later would be framed in some offices as a memory of the time when an engine that had been considered impossible simply refused to fail. Still, it was not a miracle. The run revealed subtler issues. Debate over a gasket compound that would slowly degrade under prolonged oxidative stress. A note that the oil sump needed a larger baffle to prevent foaming under sustained G-loading. The engine had held, yes, but with caveats. The team recorded each caveat as if each were a bargaining chip in a negotiation with the metal. At this point in the narrative, the team had moved from improvisation to a grimmer, more organized form of craft. They had wrestled with porosity, with thermal runaway, with oil vaporization. They had invented ducts and impellers on scrap napkins. They had introduced alloy trials and segmented crankcases. They had rewritten safety protocols after an ugly test cell explosion. And they had, for the first time, observed an endurance run that did not end in catastrophe. A day-long hold that suggested the problem might be, for the first time, tractable. But many questions remained. The endurance run was proof of concept, not production-ready. The manufacturing processes that would scale this fragile, hand-tended engine into dozens, then hundreds, required fixtures and tolerances and suppliers who could reproduce the alloy recipes on an industrial scale. The assembly line where a woman could fasten a bearing in the morning and return to the same exacting standard at night was not yet built. Logistical issues loomed. Supply chains of rare alloying elements were constrained, and the industrial furnaces that could guarantee uniform heat treatments in every batch were indefinable in their availability. The military timelines kept edging closer. Major Carter's calendar continued to exist as a sober drone in the background. More pressing to the people in the workshop were personal details. The fatigue in the night shift, the hands that had become calloused in unfamiliar ways, the letters from pilots who might never come home, and the knowledge that success meant something far larger than a signature on a log. The engine was a machine with an ethical shadow. It could save lives by enabling rescue missions. It could increase destructive capacity by enabling longer raids. The team could weigh metals and adjust tolerances, but they could not weigh the final consequences. They carried that weight in private moments, in the small rituals of shared cigarettes and the hushed conversations after a long, successful run. As the morning after the endurance run greased into daylight, Arthur walked the shop again. Machines cooled, tools were stowed. The team filed reports and packed samples for further analysis. Thomas Reed pinned his drawings to the board, his doodles now formalized into parts lists. Maria checked a lathe and smiled at a spindle run that had finally been true. Samuel, who had once carried mourning into every task, rested his hands on a crate as if feeling the instrument of his grief and his hope at the same time. And yet, the horizon of the work remained jagged. The endurance run had delivered a single undeniable fact. The engine could be kept in its operating envelope for extended periods. What it had not delivered was a plan for mass production, nor a guarantee that the same careful, handcrafted attention could be multiplied by hundreds of hands in different factories without fracturing. It had not settled the moral question of what the engine would be asked to do. It had not stopped the calendar. It had given the team a moment of quiet proof and 1,000 other problems in which to sink their teeth. They closed for the day with the knowledge that, for the first time in months, they had a tentative answer to the unasked question that had driven them. Can metal be taught to endure? The short answer was yes, under conditions of care, ingenuity, and relentless testing. The longer answer would require machines to be made not just well, but repeatably. Would require supply chains not just secured, but dependable. Would require, in the end, a consensus about what they were building and why. Outside the shop, the world churned on. Engines flew, and pilots wrote letters. New orders arrived with tighter deadlines. The workshop would have to scale its wisdom from a few faithful hands to many. And the next part of the journey, machine testing in the air, factory floors humming with synchronized drills, and the bitter reckonings of what the engine made possible, was only beginning to come into view. Inside the hidden workshop, metal had learned a new resilience. The people who taught it had been marked by the process, by sleepless nights, by small triumphs, and by a steadying, if uneasy, pride. They had not yet finished. They had not been absolved. They had, for a few hours in a cold testing bay, coaxed an engine to keep singing when it had been written down as impossible. The sound settled into memory, as real and as fragile as any human heartbeat. They would return to the furnaces, to the logs, to the drawings. They would press on toward production, toward new tests, toward decisions that would be made in boardrooms and airfields, and, quietly, in the lives of the women and men who had spent long nights bending metal to their will. The morning after the endurance run, the workshop did not celebrate with speeches. It reorganized. Drawings were reissued with tight notes in the margins. Jigs and fixtures were designed with the same obsession the shop had shown to a successful test. The problem had shifted from whether the engine could be made to whether it could be made the same way, again and again, by other hands in other places. They began by turning the innards of their small handcrafted beast into documents. Thomas Reed drafted production blueprints that were almost liturgical in their clarity. Views and sections, torque calls, finish notes. He translated the napkin sketches into assembly tolerances and made an inventory of the steps that could not vary even a little. The order of bolting flange faces, the sequence of post-weld heat cycles, the depth of a counterbore that, if off by a whisper, would bring a bearing to ruin. The act of writing these steps down was an act of restraint. It forced the team to understand which subtleties were magic and which were replicable technique. Next came the tooling. What had been hand-fitted prototypes needed fixtures that would hold parts in perfect alignment under the dull violence of production. The shop made a list: go, no-go gauges, hardened dowel pins, a set of indexing fixtures that would let a young assembler align a crankcase half with the same geometry the pattern smiths had used. The first set of fixtures was heavy and clumsy, the product of the same trial and error that had made the engine itself possible. They were filed and reworked until they fit like surgical tools. Each jig got a name scratched into a corner:
handle for the first crankcase jig, lark for the main bearing aligner. Naming them was another ritual. People tended to tools that had names. Scaling metallurgy was the trickiest enterprise. The alloy recipes that had worked in a 10-pound test coupon had to be trusted in larger pours. The foundry had to prove that it could heat, hold, and cool massive ingots to the same microstructure that the workshop had coaxed in small batches. They experimented with furnace loading patterns, with the sequence of deoxidizers, with pour rates and gating systems that minimized shrinkage. They worked with suppliers to negotiate delivery of ore and scrap with a traceability that would let them link any failure back to the barge that had carried a contaminated lot. When suppliers failed, men like Arthur called in favors, spoke to agents, and sometimes drove through the night to fetch a carload of acceptable feedstock from a neighboring plant. Quality control moved from a sketchy afterthought to the spine of production. X-ray tables were rented, then bought. Radioscopy stations appeared where apprentices once hunched over magnifiers. The shop learned to read shadows in a radiograph, tiny pinholes and microbubbles that could later open into fractures under alternating stress.
They instituted non-destructive testing routines. Ultrasonic probes skimmed the interiors of forgings. Dye penetrant revealed hairline surface cracks. Hardness maps were sketched next to part numbers. No piece left a workbench without a sticker that showed its provenance: the pour number, the heat lot, the operator initials. Training became its own crucible. Maria, who had learned the feel of microns by ear, became a teacher. She stood beside younger women and men on the lathe and beat into them the old lesson: do not trust the numbers on a drawing until the part lies in your hands and tells you otherwise. She taught the ergonomics of assembly, how to feel a bearing seat that is just slightly proud, how to coax a piston ring into its groove without nicking the surface, how to set a torque wrench so its click was the same rhythm that had come to mean this is right. The training was hands-on, repetitive, and merciless. People learned by doing and by watching the older hands correct their mistakes. There were small recognitions. A plaque commemorating the first batch that met acceptance left the shop with signatures from an unlikely roster: engineers, clerks, a night shift janitor whose sweep marks had once been the only tidy things in the place. Samuel Ortiz, who kept letters from his brother pressed into a notebook, began to teach younger technicians how to read run sheets. He taught them that a test sheet was less about numbers and more about relationships between parts, a graph of trust between man and metal. The first real factory lines were not graceful. They were rooms full of simple, repetitive tasks, each station a sacred geometry of error. Operators pressed bearings into housings. Riveters set collars. Men and women strapped each engine to a cradle for a first run. Acceptance tests were ritualized. The engine would be fitted with a minimum of instrumentation and run through a checklist that measured idle behavior, warm-up slopes, leak tightness, and vibration signatures. If anything wavered outside a narrow band, the engine went back. 1,000 adjustments might be made until it passed. Passing was banal and ritual: an intake of breath, an entry into the register, a small nod exchanged across a bench. Production brought new human problems. The pressure to deliver drew men and women from other factories to staff lines, some accustomed to textiles, others to shipyards. They brought different skills and different expectations. Supervisors had to be patient teachers and strict overseers at once. Mistakes were sometimes dramatic: a bolt torqued in the wrong sequence that warped a crankcase, a misread drawing that sent a batch of valve seats to scrap. Those failures were expensive and demoralizing, but they hardened the production culture. Lines developed rhythms, and foremen learned to read a run like a captain reads weather.
Above the production floor, the company bureaucracy began to creep into the shop.
Production forecasts landed on Arthur's desk with the same certainty as a folder of invoices. Meetings were called in rooms with lino floors and coffee that tasted like boiled wire. Engineers and procurement officers argued over lead times. Major Carter paced shorter halls, his patience fraying as new directives arrived from the horseradish-pocked offices of higher command. The calendar remained a pressing force: deadlines, delivery batches, transfer orders. The workshop answered with the language it knew: fixtures, revised drawings, overtime. While the shop scaled up, test flights became the next proving ground. An engine that had succeeded on a stand had to survive the real world: vibration modes that only free air flight could create, cooling flows that changed with airspeed, and the stress of takeoff and climb. A Thunderbolt would be fitted with the new giant engine for a ground run, taxi, and, if all went well, a maiden flight. The task of installing an engine not built to a familiar pattern taxed line crews. They had to adjust mounts, align shafts, and ensure that controls reached the cockpit just as intended. The first flight preparations were dense with ritual. The aircraft, an odd, squat warrior of a plane with broad wings, taxied into the cold light of dawn. Technicians in ear protectors hovered near the nacelle. Ground crews signaled checklists in terse phrases. The pilot answered with clipped radio acknowledgments. The engine spun in its mount. The propeller cut air in an uneven hush as systems were warmed. Gauges were watched as sacred texts. There is a peculiar intimacy in a ground run before flight. Mechanics stand close and listen, reading pistons and bearings as if they were lungs. The pilot sits in the cockpit, his hands on controls that will only tell themselves where to go once lift is chosen by the air alone. The final clearance is given, and the aircraft sets to motion. Taxi tests pass. Engines pass warmed, idle, and run-up checks. Vibration levels remain within the limits the team has agreed upon. And then the pilot throttles forward and the Thunderbolt, loaded with the new engine, lifts. The maiden flight is never a clean cinematic arc. There are moments of absolute silence punctuated by instrument chirps. There are subtle corrections, small yaw inputs, and tactical adjustments as the pilot learns how power delivery feels across speed and altitude. The first climb, the liftoff, the way the plane handles a particular power setting. Each detail is a whisper that confirms or denies hundreds of hours of work in a small span of time. When the aircraft returns, the crew inspects with a ferocity that looks like devotion. Parts are examined, oil samples are taken, and smoked for signs of metal. If anomalies appear, they are noted and remedied. If none does, the return is quietly satisfying. What the new engine did to the Thunderbolt in operational terms is a matter of scope and caution. The shop's logs capture what it delivered at a human level. A plane that could reach certain altitudes with less strain, with steadier power at climb regimes the old engine had struggled with the endurance to sustain longer loiter times in particular mission profiles. Specific numbers, horsepower, climb rate improvements, maximum operational range are recorded elsewhere and, as of this narrative, remain indeterminate, pending validated data. The important point for the people who built it was less a stat line and more a felt competence. The plane came back more often under its own power from sorties that had previously pushed it to its limits. What followed deployment was a cold lesson in the dual life of technology. Letters arrived at the foundry, some from air crews thanking the machinists for equipment that had brought them home, others in the form of government dispatches requesting more engines for expanding fleets. In quieter threads, the workshop received reports of missions that had used the engine's new capabilities in ways that carried heavy moral consequence. The team read these dispatches in the same room where they had once found soot in the corners. They read them like a map of what invention could be used for.
Those who had once considered the Maker's Act as detached from the consequences now found themselves, at night, aligning engine serial numbers with mission reports and wondering where their work had ended and someone else's choices had begun. The moral dimension was not a sudden realization, but a slow accrual. Samuel kept a folder, one that began with a pilot's grateful note and, later, contained a field report of a mission whose results left a bitter taste in the mouth. Maria, who had seen a photo of a child clinging to a mother in a bombed town, kept hers in a drawer and sometimes left the lid open on purpose so the smell of oil could not replace the smell of coffee in the morning. They did not resolve the tension neatly. Some argued that enabling defensive missions saved lives. Others said that enlarging offensive reach made harm more likely. The workshop itself could only insist on craft, on reliability, on safety. The politics of application would be decided elsewhere. Back at the factory, production matured. The company folded quality assurance into every stage: first piece inspections, statistical process controls, and the slow work of building a supplier base that could meet metallurgical demands. Companies that once scoured scrap looked for refined streams of metal. Heat treatment shops were standardized, furnaces were calibrated and certified, temperature logs were kept on paper and in longhand by technicians who knew how to read a curve the way a sailor reads tides. The engine moved from the secrecy of the hidden workshop into a larger, more mundane industrial life, where the miracle was not that it existed, but that it could be made. There were setbacks.
A vendor supplied castings with unacceptable porosity that only showed after a certain number of cycles. A freight strike delayed shipments of a specialty oil additive that the team had learned to prefer. The shop responded as it always had, with small, stubborn adjustments. Engines were rerouted to other lines. Plans were rewritten. Teams worked nights to catch up. Major Carter negotiated with procurement. He ground at a ledger until deadlines changed shape. The human cost of those months showed in faces. Cheeks hollowed by a year of steady pressure, fingers raw at the knuckles, relationships thinned by the distance of long hours. Among the quieter costs was the way the shop's expertise dispersed after the war. Mechanically minded men and women who had been trained in the intense cohort of wartime production went home to non-industrial lives or were absorbed into peacetime factories that did not prize the same skills. Some took pensions. Others found their calloused hands out of place in offices that preferred suits to grease. The collective knowledge, the small tricks and fixes, was sometimes written down, often not. That gap would later make restorations and post-war interpretations of the engine difficult. Museums and restorers would search for practices that had rarely survived beyond the men and women who had made them. When the war wound down and the immediate demand faded, the engine left its wartime context and entered a different life. Engineers adapted aspects of its design for peacetime uses, for cargo work, for civilian rescue aircraft, for heavy-lift applications in industry, applications that the men in the shop had imagined during long nights as ways to redeem the engine's existence. Not every adaptation was straightforward. The same qualities that made the engine potent for military flight, large displacement, robust cooling strategies, and heavy-duty bearings, were sometimes excessive for peacetime needs. But the lessons in metallurgy, in heat management, and in mass production migrated outward, folded into designs that reshaped other sectors. A handful of engines were preserved. A museum curator, with the tone of someone who calibrates memory like a machine, negotiated the acquisition of a serviceable example. The engine sat under soft lights, its organs exposed for visitors to see. The cooling ducts, the baffled fan that had once been a napkin drawing, the stamped initials where technicians had scratched their names. Plaques told a careful story: engineering achievement, human toil, and the ambiguous legacy of wartime invention. School groups came through in organized masses. Guides recited curated lines, and sometimes a retired machinist would stand by a glass case and point out details to a small circle of strangers. Those were the moments where the craft's human origin was most clearly visible. Calloused fingerprints, nicked corners where a file had bitten too deeply, a faint pattern of oil stains where a hand had rested for decades. Not every museum visit was celebratory. There were also memorials that traced what technology had enabled. A small exhibit in the same city displayed a map and a ledger showing how payload and range had shifted with engine changes. Photographs were included, airfields, tents, faces. Accompanying texts took care not to celebrate destruction. They placed the engine within a larger narrative of urgency, of innovation under stress, and of consequences that extended far beyond the factory gates. People who had been in the workshop told different stories in different contexts. In civic halls, in retirement homes, over cups of coffee thick with nostalgia, they would tell of the nights full of sparks and the repeated failures that took on the look of ritual. They would tell of hands that learned to read a crank through touch, of their small rights, the signature on a successful casting, the cigarette stub left by a lathe that had run true. They sometimes mentioned the heavier things, the letters from pilots, the field reports that made them pause when they read them in the morning. They rarely offered tidy moral lessons. The usual themes were repetition, craft, and the strange intimacy of being entrusted with a machine that would go elsewhere and enact effects the builders could not control. In private, some tried to reconcile. Arthur, who had been a man of tools and geometry, took a job with a peacetime contractor designing heavy machinery for civilian ports. He told himself that the art of making metal endure had applications beyond conflict. Maria opened a small machine shop. She would take apprentices and teach them the feeling of microns. Samuel took up work in education, teaching practical mechanics at a technical college where the next generation learned the same quiet reverence for parts. Their lives suggested the engine's more complicated legacy, knowledge that could be used for many ends. Across the decades, the engine's design inspired others. Patents were filed, not as claims of vanity, but as technical patches, ways to protect certain processes and to codify the improvements that had been hard-won at the stove of the hidden workshop. Some innovations were mundane, a new oil scavenging route or a revised valve seat method that reduced wear. Others were conceptual, the idea that segmented castings, bolted and welded in specific sequences, could yield more predictable grain orientations in high-stress junctions. These were the sorts of advances that fed into the architecture of peacetime manufacturing, and they allowed future engineers to stand on the shoulders of nights the original team had endured. There were also legal and commercial aftershocks. Companies that had supplied alloy elements found new markets. Engineers who had cut their teeth in the program were recruited into universities and into private industry. The hidden workshop, as a concept, became a kind of myth, the place where ingenuity met necessity and pushed past the constraints of the time. Documentarians and historians would write about it, sometimes with romantic brushstrokes, sometimes with a clinical eye. The true texture remained in the notebooks and in the hands of the people who had done the work. At the center of any telling was the human ledger. The shop's memorial book, kept in a tin box on a high shelf, contained signatures and short notes. A name and a date, sometimes a terse congratulations, sometimes a mention of someone who had not returned from war. There were small tragedies, an injury that had left a man with one hand less deft, a seamstress whose husband had never returned. There were quieter victories, letters from pilots who had, after the war, visited the shop to shake hands and to say that the engine had brought them home. Those human strands were the warp and weft of the story. They resisted tidy summation. Toward the end of the line, the workshop grew quiet in a way that felt like settlement. The frenetic nights gave way to a steadier day rhythm. Engines were produced with less improvisation and more verified procedure. The hiddenness of the shop faded. It had become, in many ways, part of the industrial fabric. When the last batches were delivered and certificates of acceptance signed, people came in and took photographs of each other with engines that had once been monumental trials. They set down the tools that had shaped their lives and shook hands with people who had been strangers a year before. A few years after production peaked, a reunion was organized. The company rented a hall and invited everyone who had spent time under the forge's light. They gathered with the air of veterans of a particular kind of craft. Arthur, now older and slower in his movements, looked out onto a room filled with faces he had once overseen. He thought of the nights, the noises, the crack of a test stand, and the smell of burnt varnish. He thought of letters read in dim corners, of a photograph in his pocket of a younger self beside an apprentice class. There was laughter and there were moments of silence when someone would mention a lost comrade and the room would become a place of collective remembering. In the final speeches, brief and intentionally unsentimental, someone said that metal had been taught to endure. Another person corrected them gently. It was not so much that metal had been taught, but that people had learned how to make conditions for metal to keep its promise. That distinction mattered. It put the work back into the realm of human agency and commitment. The hidden workshop story has 1,000 small endings. Machines were boxed and shipped. Manuals were filed in archives. A few engines were cannibalized for parts. Others preserved in museums. Some given to universities for study. The people who carried away the skill left fingerprints across industry in ways both visible and invisible. The name of the engine, the giant heart that the Thunderbolt had required, entered technical literature, referenced in papers and in patent footnotes, always with some caveat or indefinito beside a number when writers hesitated to claim a precise figure without verification. If there is a moral that the builders favored, it was a humble one. Craft matters. It leaks into policy and power, sure, but it is also a kind of ethics of practice. You make something well because you can, and because making it well is a refusal to accept the shallow answer. The men and women in the shop had learned that in the act of repeating a process, you refine not just the thing you make, but the people who make it. That refinement can have outcomes you cannot control. It can also mean that when a machine fails, it does so in ways that spare as much as possible those who depend upon it. The engine's role in history is complex. Where it lengthened reach, it also demanded an accounting of who it served, of what strategies it enabled, and of the lives it touched. People in the workshop often expressed this without the pretension of moral closure. They accepted that their hands had been instruments in a larger enterprise, and they took for themselves the responsibility of making those instruments as honest as possible. Years later, a young curator asked Samuel to tell on camera what it had felt like to work on the engine. Samuel spoke not of numbers but of sensations. The smell of oil and flux, the dull joy of a tool sliding true, the collective hush during a run, and the private ledger of consequences. He looked into the lens and said simply that they had done a job of craft in a time that demanded action, and that they had tried, imperfectly, to remember that their making had moral weight. And so the hidden workshop's legacy settled into the world like a skein of metal filings, scattered, catching the light in ways that make patterns if you stand still long enough. The engine itself became a node around which stories turned, about ingenuity born of scarcity, about the translation of handwork to industry, and about the human costs that ride with technological accomplishment. When at last, the last of the old logs was placed in a leather-bound folder and slid into a crate for the archives, Arthur took one last walk through the shop. Machines hummed, but with a different inflection now, a quieter confidence. Maria was at a lathe, showing a young apprentice how to read a surface finish.
Thomas adjusted a drawing on a digital table, his pen moves now assisted by screens he had once distrusted. Samuel stood by a window and watched an engine being loaded onto a truck. The plane it would go to was indefinido, its mission unknown to him.
He folded the little photograph of his brother that he had carried for so long and put it back into his jacket. Arthur paused at the old crate of tools, the names carved into their handles, faint but visible. He placed his hand on them, feeling the grooves where other hands had rested. Then he looked toward the yard where, beyond the chain-link fence, the sky kept its slow, indifferent motion. He thought of the nights of sparks and the long endurance run that had held. He thought of the people who had come and gone, of letters kept in drawers, and of pilots who had written thanks, and others who had written reports that were harder to read. He felt an old exhaustion settle into him and, alongside it, a steady, careful pride. Inside the hidden workshop that built the Thunderbolt's giant engine, hands had taught metal to endure. If you found this story compelling and want to see more hidden chapters from wartime workshops and the people who built them, subscribe and explore our deep dives into the craft behind the machines.